All right, so we are going to be talking about, again, the time factor behind chemical kinetics, which really is just a fancy term for what makes a reaction move either quickly or slowly. Okay, so first things first, we're going to study the rate at which something occurs. When we say rate, we mean change in something over time. Okay, and we're going to talk about how to identify how quickly something happens in relation to when reactants are being consumed or in relation to how quickly products are being formed. Okay. The other half of chapter 14, so the first half talks about the rates of reactions, what impacts how quickly a reaction takes place, how can we manipulate how quickly something takes place. The second half of this chapter introduces the idea of a reaction mechanism. In other words, the very specific instructions as to how a reaction occurs, which includes things like intermediate states. So when compounds react, they briefly collide. During that collision, this thing called an intermediate is formed. That intermediate is very temporary and doesn't stick around for long and eventually just goes back into the products that you're trying to make. But in the reaction mechanism that we study, we can try to figure out what those intermediates are and what impact they may have on how quickly a reaction takes place / the outcome of the reaction. So 2 big focuses in this chapter. And of course, we're going to start with the basics behind how to calculate the rate of something. Cool. All right. So the first thing that we have to take into account is the physical state of the things that we're trying to react together. Physical state meaning, are we a solid, are we a liquid, or are we a gas? Is this a homogeneous mixture? Is this a heterogeneous mixture? The number one requirement of any chemical reaction that we've discussed is that if 2 things are going to react, molecules must be at some point in contact with each other. Okay? A lot of times when we do reactions, we tend to take a liquid and a solid or 2 liquids. And that's because with the liquid phase, we see that our molecules are a lot easier to manipulate, right? They kind of can get into anything and everything. They're going to be able to surround the thing they're trying to react. So that's the first factor that we have to address when it comes to how quickly something will react. If we're trying to get 2 solids to react, it's going to, by definition, take a lot longer because those 2 things have to come into contact with each other. And by those 2 things, I don't just mean the 2 chunks of metal that you might be trying to put together. What I mean is that every piece of the one object has to come into contact with every piece of another object, right? So every individual molecule has to collide. So when it comes down to it, it's a lot faster to get gas molecules to do this if they're reactive. But the problem with gas molecules is a lot of times they're unreactive, right? They're pretty happy, they're pretty stable. So we kind of default to solid-liquid interactions or liquid-liquid interactions for a reason here. Okay? Another is going to be the concentration. If you have the really great concentration of something, you're going to be able to perform more of the reaction than you thought. If you do not have a lot of your reactant, then you're not going to see a very large amount of product come out. Concentration will affect the rate of a reaction in that if you have more molecules, you are more likely to see them collide. If you have fewer molecules, it's going to take a little longer. The last, and I would say, well, not last, but I would say one of the biggest factors is going to affect the rate at which a reaction will occur is going to be temperature. Hopefully this one just kind of makes sense to you on an intuitive level because we've talked a lot about how temperature affects molecule movement, right? So the hotter the thing is, the faster the molecules are moving. The faster they're moving, the more likely they are to interact with other molecules, right? High speed means high collision. High collision means reactions happening. So at higher temperatures, we're going to see that our molecules will interact with each other more often. I have one more, and it's one you may or may not recall from biology. Anybody remember the term catalyst?
Yes.
You've heard the term catalyst, right? What does a catalyst do?
Speeds up a reaction.
Speeds up a reaction. Do you remember how?
By asking it nicely in there.
By asking it nicely, I like it. No, the presence of a catalyst is kind of an intense thing. We will talk more in depth about catalysts towards the end of this chapter. But in reality, what a catalyst does is it kind of creates like a bubble or a targeted area for a reaction to occur. So think about the difference between having a location that's dedicated to your reaction, right? Let's say your two reactants know that if they find this catalyst, they've got a guaranteed location where they're going to interact with each other and form the products that they're trying to make. Okay? Versus just kind of dumping them all in one little area and saying, well, I hope you guys find each other. Good luck. All right? There is a difference. One of those provides like a bubble for the reaction to occur, and that's why it's quicker. Because then our reactants know that if they get in that bubble, they're going to be able to do the reaction. And once they're done, they leave, new reactants can come in. So a couple of things about catalysts. One is they are reusable. Okay, so they're never used up in the course of a reaction. That's the first thing about a catalyst you need to remember. They are not part of the chemical reaction itself. They are reusable. Okay, so they're always, if at any point they are manipulated in the course of a reaction, they're always reformed to their original form by the end of the reaction, so that the next set of molecules can come in and use them again, and over and over and over again. Best example of this is going to be the enzymes in your body that create the proteins you need. Okay? Those enzymes are catalysts because they're never used up. They can be used multiple times, and they're there to speed up your reactions. Now, on the macromolecule scale, think big proteins in your body. It makes sense that catalysts are in this big form of an enzyme, also a very big protein, because you have a lot of very big molecules in your body. We're not talking you've got like tiny molecules that have to interact with each other in the human body. It's a lot of very big, very dense molecules, right? And so with those molecules, if they can find a place to interact, then they know they're finding A, the right partner they need for this particular reaction, and B, they're finding a place for it to happen quickly. So catalysts also increase the rate of a reaction. All of the things we've talked about just now are things that are typically going to increase the rate of reactions, right? We're talking about having higher concentrations to increase the rate, having higher temperatures to increase the rate, having a catalyst present to increase the rate of a reaction. Okay, if we want to decrease the rate of a reaction, we really only have a couple of things that we can manipulate, and that's going to be the concentration of our particular reactants, and that's going to be the temperature of the reaction that is taking place. All right, from there we talk about reaction rates. Think about any chemical reaction we've done. Over the course of that reaction, we can measure how much is taking place or what is taking place at every different time point if we want to. We don't generally do that because we haven't studied chemical kinetics so far, but at different time points we can see that a reaction is taking place if we monitor the molarity or the concentration, if you will, of the present different things. If we're looking at the molarity of the reactants versus the molarity of the products that are being formed. In this particular reaction, we're seeing A become B. Very simple reaction, A to B. In the first part where nothing has happened because we're at 0 seconds, all that is present is that first product. Over time, however, we see more and more of the reactant becomes the product, right? We see at different time points we have different concentrations of each different thing. So again, we can monitor what's happening in a reaction by looking at concentrations at different time points. Time is going to be a big factor in this chapter. Okay, so here we have a reaction. Nice big long reaction. We have the concentration of one of the reactants, which is measured at a bunch of different time points. It looks like from 0 up to 10,000 seconds. At every different time point, we measured what the concentration of that particular reactant was. Okay, so we see that over time, what's happening?
The reactant's like disappearing.
It's disappearing, right? Does it make sense that a reactant concentration should decrease over the course of a reaction?
Yeah.
It does, right? Because it's being used to create the product. How we calculate the average rate is we take the concentration change divided by the time change. We're going to get used to reading a couple of different types of charts like this. This one is going to be a reactant change over time. We can look at product change over time. We can look at a reactant and a reactant, like two reactants side by side. We can look at two products side by side. We can look at both at the same time. It's a little weird. But in order to calculate the rate for any part of this type of data, we're going to take the change in the concentration at 2 points divided by the change in time over those 2 points. So if you do the difference here divided by the difference here, you should get this rate. Rates will be recorded in this particular section of the chapter in molarity per second. Capital M, remember, is molarity. More often than not, moving forward, you will see our concentrations are either reported in molar amounts, so just straight moles, or they are reported in molarities, capital M, so moles per liter. Specifically, that is because we will typically be dealing with volumes in liters, right? Volumes of liquids, if you will, or volumes of gases. Okay. As the reaction proceeds, we already said we saw the concentration decrease, but what happens to the rate of the reaction?
It slows down.
It gets smaller and smaller. Why?
Well, because there's less reactant basically to go around, so it's less likely that more reactant is going to react with the other reactant.
Absolutely. Over time, we're decreasing what's even available to react. And because we're decreasing what's available to react, remember we said one of our effect on the rate of reactions was the concentration. If your concentration gets lower and lower and lower, then the rate of the reaction must be slowing down. So that's what we're seeing here. Nice, Chase, nice. Like it. As we move forward, there are fewer and fewer molecules left to react. Could we mess with this? If I added more reactant, what would happen to the rate? It would shoot up, right? If I was like, okay, I'm going to add another molar amount, 1 mole per liter, my rate should shoot right up. Absolutely. Okay. Over time, we can take the change in our molarity and we can graph it versus time. So molarity on the y, time on the x. And we see that we get some kind of a function, right? Some kind of a function. And we will be messing with graphs a lot in this chapter. In this particular case, what we're seeing over time is that as things are reacting, we're approaching 0, right? So what kind of a function is that? Anybody remember?
Well, I feel like it's like exponential, but in reverse.
Logarithmic, right?
Yeah.
Haven't you guys heard that one before?
Oh, yeah, that's it.
A logarithmic function will approach 0 but never actually reach it. What is the other term for it? Isn't it an asymptote? It's an asymptote, yeah. So, as this goes on and on and on, eventually would it probably reach 0? Yeah, but it'll take a really, really long time. And according to the data that we saw in that previous table, it was 10,000 seconds. Sounds like a really long time to monitor a reaction. For our sakes, we will never monitor a reaction for 10,000 seconds. We'll probably stop at like 10, 15 minutes. That being said, over time, we can measure instantaneous rates. The instantaneous rate is at a specific time point, right? So at 0, the instantaneous rate is going to be nothing. It's not moving yet, right? We can look at instantaneous rate at specific time points using a graph like this. All I have to do is take the concentration divided by the time to figure that out. So there's a couple of different types of rates that we're going to be calculating. One is going to be over 2 time points. One is going to be at specific time points. Those are called instantaneous rates. When we say instantaneous anything, think like the radar gun that the cop is monitoring your speed with, because it takes an instant shot of what your speed is at that time. Same idea here. I want to know at exactly what time the concentration is. So if I ask you, using a graph like this, what is the concentration after 500 seconds has passed, you can extrapolate that data. That would be an instantaneous rate interpretation. Okay. Over time, all of them are supposed to slow down. Reactions are not supposed to speed up over time. They are supposed to slow down. We talked about the logic behind it. This only applies if you are not adding more of the reactants every minute or so, right? This only applies if you sit the reaction in a beaker and walk away and just monitor what's happening over time. Yes?
So they'll slow down over time
unless you're doing something to speed them up, yes. Unless you are messing with that. Yep. For us, we're going to say the best indicator of how quickly a reaction will move is at the very beginning of its reaction, right? So at the very beginning, when we put everything together, if we measure the rate right then at time point 0 or 1, then we're going to get the best idea of what the rate of the overall reaction is going to be. Okay. For our next interpretation of reaction rates, as something is disappearing, we can also interpret it as having something appear. So the negative reaction over here, so we see negative change in concentration of a reactant over time, is going to equal the positive change in product concentration over time. So as this disappears, this appears. Does that make sense? Kind of, sort of? Now, will these always equal each other? Absolutely not. Remember that there's multiple things happening here. We may be only producing half of this for every one of these, depending on the coefficients of the equation, right? For this particular example, as one of these disappears, one of these appears because of the molar equivalency here. Remember the 1s and the 2s. Coefficients. So this works because it's a 1-to-1 ratio. What happens if it's not a 1-to-1 ratio? We can predict what the rate will be. And I'm going to show you how to predict it. But for now, what you can see is that as 2 of these are being consumed, 1 of these is being produced, or 1 of these is being produced, which means that for just I, half of whatever is being degraded is going to be produced on the right side of that equation. Again, we're going to look at a better way of interpreting this, aka the formula for it. But this is just our first example of how to incorporate our coefficients. Here we see a better way to do it, okay? So we have coefficients, which are going to be the lowercase letters, not the little letters. The lowercase letters are my coefficients. The capital letters are going to be the actual compound. And when we want to predict the rate at which something is happening, we can use this formula. So if I want to know the rate at which D is appearing compared to the rate at which B is disappearing, I can write negative 1 over B times the change in the concentration of this particular reactant over time is equal to 1 over D times the change in the concentration of D over time. You don't have to write all of them out every single time. You can relate just two things if you want. Yes? I would say, yeah, you're going to want this. This is going to come back to get you. Yeah, you're right, slow. It's okay. Absolutely get this written down somewhere so that you know.
You know what they say, pictures worth 1,000 words. In this case it is.
Okay, so now you can answer a question like this. What is the rate of appearance of C with respect to the reactant A? I want you to write it down. Write the question, and then write the answer, because you will be doing this in your practice. So now we're going to use that to do this. Gotta remember, I'm taking a video, not taking a selfie.